Okay, so what are the problems with it? What are the problems with the fully complementary CMOS logic here? As we said, these are the dimensions along which we compare. How simple is the logic? How easy is it to implement different gates, different building blocks using that particular logic? What are the delays? What are the power dissipation? How is it sensitive to noise? And how does it scale? As you build more complex gates, so how does that particular logic scale here? So these are the questions that we look at, and this particular logic has problems. As you can see here, doesn't scale that well. Either the pull-down network becomes huge and the sizes become large, or the pull-up network becomes, because it's fully complementary, and doesn't look very simple. You require basically 2n number of transistors for a 2-input gate, n here and n here, so 2n number of transistors, and the PMOSs are, of course, are larger in size, and they have issues. So yesterday we were, day before yesterday, we were looking at this particular logic here, and we said that pseudo NMOS logic has advantages, but it had power dissipation, and in an effort to solve some of the issues associated with pseudo NMOS, we looked at the name in that particular one was written incorrectly. It wasn't differential cascade. There's a frequent error that creeps in, cascade and cascode. So it's a differential cascode voltage switch logic rather than cascade. I think in the last lecture I had shown that this was written as cascade. It's not cascade, it's cascode here. So we had looked at this particular logic. By the way, whenever you hear the word cascode, the cascode refers to the drain of one transistor is connected to the source of another transistor. That's the cascode connection, if you recall from your E210. And it's differential in nature because of the output here and the output here, they swing in different directions. When this is going high, this is going low, and vice versa here. All right, so we had seen this particular logic, and we had started to look at another logic which seemed to be very promising, which is a pass transistor logic. So the idea was that with the help of switches, if we have switches here, we can very efficiently, it seems, we can implement the logic here. For example, a XOR gate, one can see here, requires only 2 switches here. If the inverters are available to you, then it requires 2 switches here as compared to this particular implementation that you see here. And similarly, we were looking at, if you look at 4:1 mux, the implementation again is looks fairly simple here. So the idea was that why not you take these kinds of implementations and implement the switches using the transistors here. So the first case is where we try and replace the switch that you see here by an NMOS transistor. And we had a discussion earlier when we were starting to look at NMOS and PMOS transistors, that the NMOS transistor is pretty good when you want to transmit a 0. For example, let's say I have an NMOS transistor here, and the other end is connected to some node, and let's say the node has a capacitance here, and say the node is charged to 3.3 VDD. So initially the node is high, and then you connect it. This is supposed to be a switch, and you turn the switch on by applying a voltage here, and you want to discharge this particular node here. You want to pass a 0. So this node was initially 3.3, and now you want to pass a 0 here, so you want 0 to come over here. And we can see here that the NMOS works pretty well. Why it works pretty well? Because I have a gate, this acts as a source, I have a gate to source voltage which is 3.3, large gate to source voltage here, and this is 3.3, a current flows in this direction here, and the capacitor basically discharges to 0 because the transistor remains on. So it's pretty good. NMOS transistor is pretty good in passing a 0. It passes a 0 to this particular, to the other node here. On the other hand, if let's say this particular capacitor was 0 volts here, or 0 logic level, and we connect it through a switch again, and we want to now pass a 1. We want to charge it up to 1, charge it up to 3.3 here. Now what happens is, note that when you want to charge, this acts as a source here. This node acts as a source. This is 0 and 3.3 here. So initially gate to source voltage is 3.3 and a current flows and it starts charging. And it keeps on charging till about the gate to source voltage drops to about threshold voltage. So here note that gate to source voltage has become threshold voltage here. Now once that happens, the current begins to drop rapidly. The current begins to draw rapidly here, and we had shown here earlier how the drain current changes with gate to source voltage here. So the current begins to drop, and the voltage doesn't rise very rapidly now. So before you reach threshold voltage, the charging is pretty fast, but once you reach the threshold voltage, the charging current available is small, and this node here, if you're talking about short intervals of time, the node here gets stuck to a value close to 3.3 minus VTN. So if I have VTN of 1 volt, the node here will become, it will drop to 2.3, and then it's not able to charge beyond that, or it charges very slowly here. So we had wanted this particular node to become 3.3, but what you end up getting is only maybe 2.3. So it's not able to, NMOS is not very good in passing a 1, taking a high value here and then passing it to the other node here. All that you get is, if you have a 1 here, and if it's 3.3, we can call it a strong 1, because it's right up to VDD. And at the other end, all that we get is a weak 1. You get a 1, it is 2.3, it is high, but it's a weak value here, because it doesn't reach to its full value, which is 3.3 here. You get only 2.3 here. So you get a weak 1 here. All right, so that's, so NMOS has that particular problem. So if I'm looking at implementing the switches using NMOS, so whenever if A is 0 and let's say B bar is 1, well, the value of A will get communicated here properly. 0 will get properly here. But on the other hand, if A is 1 and I'm implementing it as a switch, and switch is again closed, so instead of 3.3, I'll get a 2.3. So it doesn't pass the 1 value properly here. And as you can imagine, that if I look at the PMOS would be complementary. The PMOS would be complementary in the sense the PMOS would pass a 1 properly and will not pass a 0 properly. Okay, so it's just complementary. So now what is the problem with this? So if I start using this as a switch here, NMOS as a switch, so I get 2.3. So note that now this part here will serve as the input to some other gate. And note that if you get 2.3, this output may go to the gate of some particular switch here. So if 3.3 minus VTN we get here, then we end up getting 3.3 minus 2 VTN. So the problem can get compounded. As you cascade one gate to the next, 3.3 minus VTN, so you get 2.3, and then you get 3.3 minus 2 VTN, so you start getting into a problem. As I said, if you use a PMOS, PMOS has the same problem. PMOS passes a high properly here. So if you have a node which is charged to 0, you apply 3.3, the node will get charged to 3.3. No problem. On the other hand, if I have a node which is 3.3 and you want to pass a 0 to it through that switch, then again it doesn't pass. It stops after it reaches a threshold value here. So PMOS is problematic in terms of passing a 0. So it makes sense. You may imagine that if NMOS is very good in passing a 0 and PMOS is very good in passing a 1, then maybe we can combine them together and then we'll have a better switch. Okay? So that's the idea behind what we call as the transmission gate. Yes?
In the NMOS case, when you are transferring 3.3,
yeah.
if it does to the next stage, then it will also be 2.3, right? So what I'm saying is...
No, so 3.3 minus VTN, right? So you get 2.3. This 2.3 may end up going into the gate, let's say. Right? So that's what we are showing. So if it goes into the gate, now up to what value will it charge? Right? So now it will charge up to only 3.3 minus 2 VTN. So the problem gets compounded. Okay? So that's what we're saying. So if you want to avoid this, then what you'll have to do is, as you'll see, you may have to, after this, you may have to, it charges only to 3.3 minus VTN. You may have to put something after that to restore the value back to 3.3. Otherwise, the problem gets compounded. All right, so the idea was then why not take a NMOS and take a PMOS, combine them together, and so the NMOS will be very good in passing a 0 and PMOS will be very good in passing a 1. And therefore, a combination of NMOS and PMOS, which we call as a transmission gate, and sometimes this particular symbol is used for short. And so you can see here, if I put C equal to 1, then C bar is 0, so both PMOS and NMOSs are on. Okay, if this is 1, then this is 0, and this is a PMOS, so with a 0 here, the PMOS turns on and NMOS also turns on, and the switch is on. And whether it's I have a 0 here or a 1 here, it will pass nicely, because one of these transistors is good in passing at least one of those logic values here. So with that, then you can implement with this transmission gate, you can implement now, so it's a good switch, and you can implement the different logic that we saw earlier here. So for example, you can see that this forms a 2:1 mux here. And you can similarly verify what this particular operation is, AB bar and AB, so you can check it out. So you can implement things in this particular manner here. But there is a problem. Fine, so we have a good switch now. The problems are, of course, the switch is much more complicated. I have an NMOS and a PMOS, and PMOS takes up large area. And not only that, the capacitance at each one of these nodes becomes large. The capacitance at this node comes about from an NMOS and as well a PMOS. So the capacitance becomes large. And so we'll see. The other issue is, fine, we have a gate like this. Let's say we have a multiplexer, and we have, let's say, another gate like this. And when you make circuits, you'll cascade one gate after another. You'll cascade a number of gates. And when you cascade a number of gates, this particular logic, this pass transistor logic that we are talking about, has a problem. Note that, let's say, I have one transmission gate and some capacitor loading is there, 5 femtofarad. 2 pass transistors you put in series, 3 you put in series, and then 4 of them you put in series. And then, as you make more and more complicated logic, you'll have more and more number of pass transistors in series. Now just focus on the delay, any one of those delays here. Let's say the top part here. So one pass transistor, so let's say initially this is 0, and you apply a 0 to 1, and so the capacitor charges up and charges through the resistance associated with the pass transistor, and you get a delay of 69 picosecond. You put 2 of them, you get a delay of 165. You put 3 of them, you get 285. You put 4 of them, you get 439. The delay is not linearly increasing with the number of pass transistors that are there. If I plot delay, the delay increases rapidly with the number of cascaded stages here. The delay has a n-square component also. So there is a constant part, of course, some intrinsic delays and all that. Then delay increases with the number of pass transistors in my network, and also increases as an n-square. So this is problematic. As I'm building more complicated logic, the delay increasing as n-square is problematic. And so the way one can break that, if you look at these pass transistors, a number of them connected in series with some capacitance here, you can build a very simple RC transmission line model. RC, you can build like this, and it's easy for you to quickly see that the time constant for this one would be if you look at one capacitance at a time, this C sees only 1 R, this sees 2 R, and then this C will see N R. And so RC into 1 plus 2 plus N, and you can see RC N plus N squared. So that's the origin of why my delay had a linear component and had a square component here, N and N squared here. So this is problematic. So as I build more complicated logic, my delay is increasing, not just with the number of gates. N would be proportional to number of gates. It doesn't just increase with the number of gates that have been cascaded, but increases in square also. So this is problematic. So what can be done is, frequently what I can do is, if I have a large chain of these transistors, transmission gates in series, what I can do is I can break it up in the middle. I can break it up in the middle and let's say put a buffer here. If the delay is becoming very large, n and n plus square, so you break it up in the middle and add a buffer, So now let's say I had n transistors in series, n transmission gates in series. We break it up into n by 2 and n by 2, and in between we put a buffer. So now if you look at it, effectively what is happening is this. You have one transmission line, RC, RC, RC here. Then you have a buffer. Buffer, in simple terms, two inverters in series. Two inverters in series, so that's a buffer here. And then this is another RC, RC here. So what happens is, you've broken the transmission line into two parts here. This will have a delay of, let's say, this will have a delay of RC1 plus 2 times n by 2. And this will have another n by 2, so 0.5n and 0.5n square. And overall delay would be, overall delay with the buffer would be tau equal to 2 times n by 2. N by 2. So this is an n by 2 transmission line, this is an n by 2 transmission line, and then in between there's a delay due to the buffer. And so this breaking up of a large chain of cascaded transmission gates through buffers can potentially help you to reduce the delay, provided, as you can see here, the earlier delay was tau n, a transmission line of size tau n. Now the delay is 2 tau n by 2 plus tau buffer here. And if the transmission line is large, what you would find is, if you do the calculations, let's say if you put here some 20 or so, n is 20 and you put 10 here, so you can calculate 2 into delay of this. This delay is much smaller than this particular delay because of the n square effect. And if the buffer delay is not too large, what you end up getting is that this becomes more efficient. So instead of cascading a lot of these transmission gates one after another, what it is suggesting is that you break the chain in between and introduce a buffer. And you'll end up getting a reduced delay. Now, you may further say, well, why not break this further up into two transmission lines, one by n by 4, another by n by 4, and in between introduce a buffer. You can do that as well, provided you end up getting an improvement in delay. All right, so you can, depending on what the values of n's are, you can frequently break your chain of transmission lines and introduce buffers in between. Buffers in between to manage the delay values here. So if you continue thinking along those particular lines,
Sir,
yes.
can we not replace this buffer again by a capacitor and resistor and it will be same as before?
Can this buffer?
Yes.
No, so note that what is happening is, if you look at here, there is a signal, let's say a signal which has made a transition, right? So it goes RC, RC, RC here, and then when it comes here, all that it sees is a capacitance at the input. It sees as a capacitive loading and it stops here. Then a fresh signal starts from here, from VDD. A fresh signal VDD, so from VDD you will see a pull-up resistor and then it starts like this. So the chain has been broken. The chain which was earlier one long chain, one continuous RC. So for example, if I look at a capacitor here, earlier a capacitor here, if you go back, earlier a capacitor here would have seen this R and would have seen all these R's. All of these R's would have come, all of this here. Now this capacitor is charging through here, through VDD. It's charging through this path, particular path here. Okay? And that's why we have written this delay of this particular part is a transmission line which is n by 2. This is also n by 2, plus the delay of the buffer. So that's how the overall delay now it comes into picture. And as I've been saying, if this tau n by 2 can be considerably smaller than tau n. And that's where you get the benefit of breaking the transmission line. Okay. Now one can carry this argument further, and this is saying if I have a long chain of transmission lines at frequent intervals, introduce buffers to keep the delay manageable. One can carry this argument further and say, well, why not, at the output of each here, for example, when we look at a transmission gate here, this one, why not at the output of each one, whenever you are implementing a logic, put an inverter? If at the output of each one I put an inverter here, then there is no such long chain. It will never happen. But then it becomes more complicated. Each one of them has one more inverter attached to it. So that long chain, long RC transmission line will never happen because every time there is an inverter in between that is there here. So look at this one. The other one is, note that in our, by the way, what function does this implement? What is the function implemented by this? Anyway, while you're figuring it out, I mean, note that if you examine this logic here, pass transistor logic, you see that at several places you require S bar, A bar, B bar, you know, the inputs and their complements are required here. For example, if you look at a transmission gate, if there is an S, there's an S bar also required, right? And as I said, this particular logic, you can make it better by putting in a inverter at the end of each one of them. If you put an inverter and then you cascade, then cascading becomes easier. You don't get a long transmission line. So you could potentially, instead of saying that after every, you know, whatever 10, I'll put a buffer, well, after every logic, why not put an inverter directly? Now if you cascade, there is no problem of a long transmission line here. Now if you look at this particular one, so I've taken the basic gate here, whatever the logic function that is performed here, and I've added an inverter. And the logic for the inverter should be clear to you, that it becomes easier to cascade. Now as I've also been saying, that everywhere you see that I require an S and an S bar, an A bar, an A, and all that. So, which means that while you are generating this, why not generate O bar also? Because it would be required somewhere else. If I try to cascade this particular one to the next gate, I would require O, output whatever it is, and I'll frequently require O bar also. For example, if it has to go to the gate of some transistor here, I'll require S bar and I'll require S also. So frequently what is done is, while you are generating this, you also generate this part here, the complementary part. You can see here is the upper part is exactly the same. If you have A bar, you get A, and if you have B bar, you get B. And the same inverter is there, so if you get whatever output is there, you get a complementary part also. So this is nothing but a mux, a 2-input mux. S is a control signal. Depending on the value of S, you get a, if S is 0, you can verify. If S is 0, what do you get? O. And if S is 1, you may get the other input here. So this is a 2-input mux. And we call this, it goes by the name of double pass transistor logic, DPL. Because it's not just a, you know, we were seeing earlier that this was the pass transistor logic here. This was the pass transistor logic. So we not only have this, but we have built a complementary part here also. Why? Because we'll require it anyway. Everywhere we'll require O, we'll require O bar also. So we built this also. And we've added the inverter also, so that it becomes easier to cascade. Now after doing all this, it's, you know, so the original idea was that we can implement logic very efficiently with switches. Now when we looked at the switches became complicated. They became transmission gate. And then when we looked at cascading, then cascading was a problem, so we had to add an inverter. Then we said everywhere complementary inputs would be required. So it's now becoming a complicated logic. So the whole advantage of the previous one is lost. The initial idea was very simple, but the whole advantage that you see here, it sort of disappears here. And also note that these transmission gates have a problem. This is a, you know, not a very well drawn layout. It was done in 2-3 minutes. And so all that I want to highlight is the transmission gate itself is pretty large because of the PMOS. PMOS has to be drawn in an N-well, and the PMOS sizes are large. And so the area is large. As I said, the capacitive loading is high. And so the original purpose is sort of defeated. When I have an NMOS and I have to connect a PMOS and I have to do all of this here, the original purpose is gone. Which means let's go back to our earlier idea that we want to implement it using switches, but I don't want to use PMOS. I don't want to use a transmission gate. So I don't want to use a transmission gate, so I'm going to eliminate the PMOS. All right? So I'm going to implement like this. Eliminate the PMOS, and I'm going to only implement my logic using NMOS. But what would be the problem? The problem would be that I will get a weak one or a poor one. The one will not be a nice one there. So now what I do is, maybe I add an inverter. So even though I may get a poor one, but then the inverter will sort of restore the logic. So it may be a poor one, but then I'll get a proper 0, a strong 0. And it passes a proper 0 here, so I will get a strong 1 here. So the inverter is being added to restore the logic back to strong 1 and strong 0. So that's the idea, that use an NMOS here, and with these NMOSs add an inverter to restore the logic back to strong 1 and strong 0 here. But it's not as simple as that. Let's look at this one here. So I've drawn a transmission gate, a NMOS gate, and I've drawn an inverter. That's what we are trying to use the inverter to restore the logic. So note that I have 3.3 and I 3.3, and because of threshold voltages and all that, I get only 1.78. In fact, because the body is connected to ground, so VT is even higher than 1 volt. Okay, so I get 1.78, a very weak one. A strong one would have been 3.3, I get 1.78. So I apply this to my inverter. And the inverter logic is 0.2. Ideal value is 0. Ideal value is 0, but I get 0.2. Maybe I can live with it, and 0.2 is not that bad. But the other thing that I get is a leakage. I get a leakage because 1.78, the PMOS is on and the NMOS is also on. And so I get a leakage. And that defeats the purpose. That I get a static leakage, which I absolutely do not want, any static leakage in my device here. So now the trouble is, the idea was that this inverter would restore my logic to proper values. Well, it's not doing that very well, and it's also causing a leakage here. So the solution to that may be, can I have 2 different transistors in my process? A transistor with threshold voltages of +1 and -1, and maybe a transistor with a threshold voltage of 0. All right? A 0 here. If the threshold voltage was 0, then, well, 3.3 would pass very nicely here. Or very low VT. Suppose I had a transistor with a VT of 0.2 volt. Pass transistor with a VT of 0.2 volt. So for 3.3, I will get something like 3 volt here. And 3 volt here would nicely get restored to 0. All right? But then I'm asking for 2 different kinds of transistors, one with a very low VT and one with a normal VT to implement my other one. Well, you can ask for it, but you may not get it. It introduces process complexity. So that's one way potentially to solve a problem. The other one is, can I solve this problem through some circuit means? Okay? So look at this alternative solution. The alternative solution is, yes, so the basic idea is, yes, I'm going to use an inverter to restore the logic, but the inverter was not restoring it very well. Why? Because the value was, go back and see, the value was 1.78, and it's causing leakage also. So what we do is, well, I get a poor 1 here, but then we add another PMOS transistor here. We don't want to use PMOS transistors, but then this is a sort of, there is no other way out. So we are not adding PMOS to every, note that it's not a transmission gate. So we add a PMOS here, because PMOS is the one which gives me a strong 1, right? So we add a PMOS here. But then the goal of this PMOS is to take this weak one and make it stronger, connect it to this particular one. So now how do I do that? Now I want to make this, I need a 0 here, right? I need a 0 here, but I need a 0 here only when this is 1. Only when this output is 1, then I need a 0 here, right? Now remember, what we are saying is, in this kind of a logic, frequently you will require B bar and all that. So suppose I implement a complementary part also. I add a PMOS to this also, and then look at this arrangement, it goes here. Now, do you see that if this is supposed to be 1, this whole part is complementary. This is A bar plus B bar. This is 0. This 0 goes here and turns the PMOS on, and it pulls it up to VDD here. Similarly, if this is supposed to be 1 here, then this will be 0, and this 0 will turn on this particular transistor here and will pull it up to here. Now, so the idea is that you build a PMOS, but you build a PMOS of actually very, very small size. Very, very small size, because all that you're trying to do is, note that you're trying to just pull it up enough so that this inverter works properly. You don't need a very strong PMOS here. All that you want is a minimum size PMOS that you can build and add this only at this particular point here. So you're not adding a PMOS at every gate. It's not a transmission gate. You don't add a PMOS here, you don't add a PMOS here, don't add it here. It's only at the output that you add at this particular point here. So it's still much more efficient than the earlier transmission gate-based pass transistor logic. You add only a PMOS here and a PMOS here. Now, so this is the logic that we are talking about. A complementary pass transistor logic here. So this is a NMOS network, and this is an NMOS network here. This is also an NMOS network here. Is driven, if this is driven by A bar, this is driven by A bar A, B bar B, complementary as you can see here. A, B, then you put A bar, B bar. And for every transistor here, there's a transistor here. For every transistor here, there's a transistor here. The same gate inputs are there. You use an inverter to restore it, and you use a PMOS to improve the one that you get here, to get a better one. So this is known as a complementary pass transistor logic, and so it's frequently used. Now, again, as you can see here, it's also sort of become not very simple. You have 2 NMOSs here, 2 NMOSs here, PMOS here, and an inverter here. It's not very simple. So let me show you some results here. This is a 2-input mux. This is taken from this particular paper. 2-input mux. Look at the complementary pass transistor logic here. One part here, another part here. Note, this is the PMOS for restoring it high, PMOS here. And what is written here are the sizes in lambda. So this NMOS is 6 lambda, 6 lambda, 6 lambda, 6 lambda here. Note that PMOS has been kept to the minimum possible size, 4 lambda here. And this inverter, the size is pretty large, 10 lambda for the NMOS and 12 lambda for the PMOS, because it has to drive the subsequent gates. This may be going to many different, there may be an interconnect length also longer, plus it may be going to several gates here. So that's why this inverter has been made stronger. But note that this is a pretty small PMOS here, a 4 lambda only. Now, so in this particular paper, they took this particular one, a MUX2, and they 2-input MUX, and they implemented it. You can count that there are 10 transistors here. The overall area was 5528 lambda square. And then they implemented the whole thing using CMOS, complementary CMOS. Requires 12 transistors, and the area was 4111 lambda square. So it didn't turn out to be, the whole idea was that switch-based logic would be simpler. It didn't turn out to be that simple. Okay? Didn't turn out to be that simple. Now, if you note, look at this particular one. This is not a regular CMOS. Can you see that? A regular CMOS would have been whatever is in the pull-down network, exactly complementary part is in the pull-up network. It's not a regular CMOS. But it's a CMOS. I mean, there's a NMOS part and there is a PMOS part here. If you note, it works very interestingly. Let me remove this particular part here. A device like this is what we call as a tri-state inverter. Normal inverters have outputs 1 and 0. Tri-state means there's a third state, and the third state is what we call as the Z state, which is the open circuit stage. That the output is floating. Okay, so it has 3 states here. You can see if S is 0, if S is 0, the pull down path is cut off. This is 1, the pull up path is also cut off, and the output is floating. Okay, so that's the third state, the floating state. If S is 1, then this is 0, then of course this is enabled. And if A is 1, then output goes 0. If A is 0, the output goes 1 here. So it's act like a normal inverter, except with a control input of S here. So if S is 1, then what am I passing at this particular state? A bar. And A bar, and then if you note that if S is 0, it passes to this particular node, B bar. And then you put an inverter to get the proper output here. So anyway, so this is 12 transistors, and you can see here 12 transistors. Counting number of transistors will get you wrong, that this is, it may give an impression that this is more efficient, and in fact it's not. Now, of course, you may be wondering, why is it not so? If I have 12 transistors here, these are also, you can see 9 lambdas and all that. Why is this taking up lesser area as compared to this particular one? So the layout is not just the area, but it's also symmetry in the circuit. Symmetry in the circuit or regularity in the circuit reduces area here. So this is what they had. They've given the layouts of this is your CMOS, and this is your complementary pass transistor logic here. And what they're commenting is that the lack of regularity. It's not a very symmetrical. Complementary pass transistor logic is not as symmetrical as this one here, and it ends up you don't get very efficient layout. You end up wasting spaces, empty spaces at various places, and because of that, you don't end up getting a efficient implementation here. So this one still turns out to be more efficient as compared to this one here. All right, there are other versions of this pass transistor logic. In this case, they are trying to restore. So the idea was to restore, instead of weak one, you get a better, stronger one here. So what they do is they take these inverters anyway, and they connect the inverter to here, and they connect the output of the inverter here. So if this was supposed to be 1, this was supposed to be a weak one, and this was supposed to be 0 here. And so this 0 will generate a strong one here, and then we'll pull this particular node up. But there are many such versions of pass transistor logic, different ways of making a weak one into a strong one, right? And using this, but it's a little bit of a, I would say there are people who still argue that this particular logic can give you, in some cases it does give you more efficient implementation. People have implemented multipliers and all that in some cases. But the original argument that I showed, it seemed very attractive. It seemed very simple. You can see that it's not. After you try and solve all those problems, it's not as simple as one had imagined.